the applications of Gauss law. Second example, to calculate electric field due to a uniformly charged plane sheet. Suppose we are having a plane sheet like this which is uniformly charged. Suppose it is positively charged. Then on this side, the electric field will be coming outwards like this. And here, the electric field will be in this direction. So suppose we need to calculate electric field on either side of the sheet at a point which is at a distance x from the sheet. So we'll draw the figure. Suppose this is the uniformly charged sheet. Suppose it is positively charged. And we need to calculate electric field at this point P. And this point P dash. Distance of these points from the sheet is x. So both these points are equidistant from the sheet. Now what is the first step we need to do to calculate electric field? Yes, we need to draw the Gaussian surface. So as shown in your textbook, you can draw a rectangular Gaussian surface also, and you can use a cylindrical Gaussian surface also. I am drawing a cylindrical Gaussian surface as it's easy to draw a cylindrical Gaussian surface. So suppose this is our Gaussian surface passing through point P and P dash. So this is our Gaussian surface. Now, we need to calculate electric field, and there are basic 3 steps to follow to calculate electric field. First is to calculate the charge enclosed in the Gaussian surface. So I'll show you this figure how it looks in 3D. This is the cylindrical Gaussian surface and this plane sheet will be like this. So the surface will be passing through the sheet. Now, we need to calculate in first step the charge enclosed in the Gaussian surface. It will be like this, cylindrical portion. So what is the charge enclosed in this? How we can calculate that? From the formula of surface charge density. Sigma. What is the formula for sigma? That is Q upon area. So from this equation, we get the formula of charge, and that is sigma into A. So our first step is over. Our second step is to calculate flux through the Gaussian surface. So the formula for flux was summation of E dot delta S. Now, here we are considering 3 portions from the Gaussian surface, and we name the fluxes as phi 1 plus phi 2 plus phi 3. Suppose the flux we calculate through this portion. I am naming it as phi 1. Now, which is this portion? Just see. This is the Gaussian surface. We are talking about this portion of the Gaussian surface. Now, as the electric field of the sheet was coming outwards, so the electric field will be in this direction. What will be the direction of the area vector delta S? As this is the area vector is perpendicular to the surface. So area vector also will be in this direction. So both electric field and area vector are in same direction. So from here, this is the direction of electric field, and same is the direction of area vector also. So what is the angle theta for this? The angle theta will be 0. So this will be phi 1. Now from this portion, whatever flux we will calculate, I am naming it as phi 2. So that is for this region. Again, here the electric field will be in this direction, and if this is the area, then the area vector will be perpendicular to it. So again, the angle between electric field and area vector is 0. So this is electric field, and this is the direction of area vector. Again here theta is equals to 0. Now the remaining portion, this portion, that is the curved surface of the cylinder. So suppose I am considering this area. So the area vector will be perpendicular to the area and the electric field will be again in same direction, this direction. So if I am considering this area, then this will be the area vector and this will be the direction of electric field. Just see the angle here. So your theta is equals to 90. Now I will calculate total flux. Phi 1 plus phi 2 plus phi 3. Suppose if I calculate phi 1, so what I will get? From this equation, summation of E delta S cos 0. What about this? Same phi 2. Summation of E delta S cos 0 plus summation of E for phi 3. Summation of E delta S cos 90. Now, what is cos 0? That is 1. Again, cos 0 is 1 and cos 90 is 0. So, what I obtain is summation of E delta S. I'll write it like this. E summation of all delta S plus E summation of all delta S. And this will give me 0. Now, if I do summation of all delta S, then what I will get? See, this portion 0 was this, that is phi 3. For this is the region, this one, whole curved surface of the cylinder. So wherever if I calculate the flux, either here, that is this point, or here, or here, or here, here, anywhere, if I calculate the flux, I am going to get answer as 0 only. So this whole curved portion gets cancelled. So the remaining delta S is this portion and this portion. That is, these two portions are only remaining. So if I add all the delta S, then I am going to get the area of this cross section, and that will be written as A. Same way, this is the area of cross section of this portion. Okay, so this will give me 2EA. So this is my equation 1. Now the third step is the formula for Gauss law, and the formula was flux is equals to sigma q upon epsilon naught. What is sigma q? Sigma q is the charge enclosed within the Gaussian surface. This charge enclosed in the Gaussian surface will be the charge enclosed in this much region, and that was this sigma into A. So instead of summation of q, all q, what I will write sigma into A. So sigma into A upon epsilon naught. This is my equation 2. Now we compare equation 1 and 2 as this is also the value of flux and this is also the value of flux. So from equation 1 and 2, what I obtain is 2EA is equals to sigma A upon epsilon naught. Both this A will get cancelled. This is in scalar form. If I want to write it in vector form, then I'll make a vector sign over here, and here I'll write a unit vector along the direction of electric field. Okay, so this is the equation of electric field due to a uniformly charged plane sheet. Suppose this plane sheet is positively charged, then the electric field will be coming outwards, and if the sheet is negatively charged, that is if this sigma is negative, then the direction of the electric field will be towards the plate like this. And this equation which we have obtained does not depend on the distance of the point from the sheet. This is very important. See, here this x is not present. So the value of electric field does not depend on this distance. One more point. This equation which we have obtained is true for the middle portion of the sheet. That is the middle portion of the sheet, which is away, far away from the outer edges.